Okay, in the third part, we are gonna study some properties. Maybe we can try to discover the properties or the definition of the exponential function. But now we are gonna use that to do the math and hopefully makes our life easier. Okay, now that we have just defined new operation, let's see if we can derive some basic properties based on the definition. And notice the word based on the definition. Because again, usually you are given a list of properties which you can find if you want to. You can skip to this page. There are like more than five, but the first five are there. But let's see if we can, prove or discover that ourselves from scratch. What is m to the power of a plus b? So if you read the word, it asks, okay, you are asked to multiply m by a plus b times. So you multiply the same number by some amount of copy. And so this, by the definition, it means we have to keep multiplying until we have a plus b copies of m's. That's how you expand that. And can we simplify that or make it easier to think about? Yes, because since this is just just a sequence of multiplication, we can divide it in any way we want. So let's say we take the first a copies of m here and put a parenthesis around it, and then put the other leftover, which should be b copies. And there are a copies, there are b copies, so the total number of m's are a plus b, which is what we have above. We just group them into two separate piles. But what is this one? The first part, you multiply m 8 times, so you get m to the power of a. And then there's this symbol, multiplication, and then we multiply m by b times. That is m to the power of b. And that's how we can how we can prove the first or the most important property for exponential. So whenever you see this kind of notation, there's something raised to the power of two numbers. You think of that by definition, and actually we can split that out. And if you just skip from this step to the end, m to the power of a plus b is m to the a times m to the b. Yeah, some simple stuff. And sometimes, just to make a remark here, sometimes if you stick numbers together, since we multiply that a lot, then sometimes we can remove, or let's say discard the multiplication sign. And if you don't see any sign, you see two numbers together, and you don't see any sign between those numbers, you almost always think that what we have in the middle is multiplication. So that's the first one. And I invite you to try this before you go to the end. Okay, if you have m times a to the power of a, m times n to the power of a, what does it mean? Okay, m times n to the power of a. Again, by definition, you multiply m times n, that's the base, that's the number, for a times. Not a single time, like a time, no, but a times. And that definition, can be translated into this annotation. You have a copies of m times n. You have m times n times m times n times n times n times n times n. and so on and so forth. But then we have to use the property of multiplication, where you have things multiplied together, you can switch around the numbers however you want. So in this case, we're going to put all the m's together. And how many copies of m are there? Now there's one in the first term, there's one in the second term, and so on. And since there are a terms, and there are a copies of that, then there are also a copies of m. And then we have n, and that n also appears a times, because again each copy has a single n, and there are a copies, so there are a copies of n as well. And eventually we can see that, oh, this is a m to the a, this is n to the a. So that is that our second property of the exponential function. It's still simple enough. What about this one? This is what people they get confused. If you don't think back about the definition, it is easy to confuse these two symbols, these two statements. So let's see what is that. And again, if you read, this means you multiply m to the a before b times. There are b copies of that. And so this is the first copy. That's the second copy. So on and so forth. Then there's a last copy. So there are times. And then this is where the things get kind of like weird, because the first one says that you have a copies of m for the first parenthesis, for the first term. And then you have another m copies. Sorry, another a copies of m. And then it repeats until the end. And each one can be expanded to give you a copies of m. But the total is still b copies, or b times. Oh, I should not change the word. And if you ask how many copies of m are there, like overall, maybe it's difficult to see if we write it this way. But maybe if you write it this way, so there are b copies of m. Copies of each parenthesis, and each of them have a copies. You multiply them by a times. And then you can see that this kind of like a box. Zoom out a little bit. Yeah, there's a box. Each copy has each parenthesis, each term has a copies, and there are b terms. And so based on this image, and you can see that we have a times b copies of m. So that's the third property of exponentials. A times b copy of this base m. Which again, let me remind you again that we have earlier that if you have a plus b, then you have m to the a times m to the b. But this one, if you take a look at this one, if you have a times b, and instead you have m to the a times to the power of b. And these two means totally different things. So be sure that you don't, use one instead of the other. To the b, m to the a times m to the b. Okay, so that's the third property. Next one, I think that, there are two more. What is m to the 0? And that's kind of like a philosophical question. Because if you ask me to multiply m by 0 times, what the result would be? You have a number right? But you don't multiply at all. You do nothing. What does it mean to do nothing, and what is the result? Right? Because if you read at this definition, you might think that it is zero. Like if you start from nothing and do nothing, you should get zero. But in fact, the answer is one. Because first the nothing, the nothingness for multiplication is actually one. For instance, if you have x and you multiply x by nothing, it doesn't mean you multiply that by zero. Right? It means you multiply that by one. Like 1 times x is 1. So in terms of multiplication, nothing like is a number 1. And also if you raise x by the power of 1, again it means you raise it by nothing. And again, this is nothing. This is nothing. And so if you multiply nothing, you should get 1, not 0. But in the philosophical term, I try to explain it in this way. But another one, which gives you some concrete value, is that if you notice a pattern that you have m to the power of 3, you have m times m times m. If you have m squared, you get m times m. If you have m to the power of 1, you get m. And then you can ask what happened the step earlier. If I go back and try to compute m to the 0, what would it be? And the answer is you have to see the pattern. Right, from mq to m squared, like we divided by m. In other words, if you have mq and you divide it by m squared, you get just m. Oh, that should be capital M. You divide it by m squared, you get m. And likewise, from m squared to m, or m to the power of 1, you repeat the same step. You divide by m. In other words, you have m squared divided by m to the power of 1, you should get m. And then if this pattern persists, if you keep getting the same pattern, then you should get m to the 0 by divide the previous term by m. So that means we have m to the 1 divided by m to the 0 should be m. And to keep the same pattern. But what is m to the 0 then? M to the 0 would be, m to the 1 divided by m. If you switch that and multiply both sides by m to the 0 and divide both sides by m. But that is exactly just m over m, which is 1. So that's the proof, quote unquote, right, of this property. And also maybe just another convincing argument is that if you have m to the 0 plus a, like on one hand 0 plus a is a, so you should get just m to the a, right? On the other hand, we just have a property that it is m to the 0 times m to the a. If we have this property, then we can show it this way that m to the 0 should be 1. And then just take a look at the left hand side and the right hand side, and you see that like they are equal only if this term, that is extra term, is 1. And so there's some arguments for the m to the 0. And there was another argument which I didn't put it there, but people ask what is 0 to the 0. Now usually you have to go to calculus to understand what this is actually asking in the first place. Yeah, but the answer is not the answer, but one answer. One good answer is it should be 1 as well. And because that's a kind of conflict here. Because we know that 0 to any power is 0. Because by the definition, the 0 times 0 times 0 gives you 0, no matter how many copies are there. But on the other hand, if you have a to the power 0, that's 1. This is what we just have here. So what is 0 power to the power of 0 then? Like what are the exceptions? Like, do we have exceptions for the first one where n can be 0? Or do we have the exception for the second one where a can be 0? And the answer is that we have this one, n cannot be 0 for this to work. Because again, if you multiply nothing, you always start with 1 and then you multiply the number. If you multiply nothing, that means you go back to the start, which is 1. And the start is not 0, the start is 1. And so that's another interesting math. We don't ask it in class, but I just thought about it and interesting enough to share. Oh, and also, if you are not convinced, you can use your calculator to compute or to graph the function x to the x. And let's see if I can pull that up real quick. So Desmos. Go to Desmos and that is once and for all. Does it give you 1 or 0? 0 to the power of 0. See? And yeah, also another convincing argument. If you plot that graph, it looks so weird, right? It drops here and it bounces up. And you can see clearly they are approaching 1. Fun fact, 0 to the power of 0 is 1. Again, you might think of it differently. If you know calculus, you might have a different idea. Yeah, it's good enough for that. Oh, and lastly, we should finish that. Lastly, we have another properties about the power of minus. At least at first, the power of minus doesn't make sense. Like it does make sense, but if you think about the power of, let's say, m squared, as you multiply m 2 times, that's what we have, right? But what if what is m to the power of minus 2? Do you multiply m by minus 2 times? And that doesn't make sense. So it's not this one. But another way to interpret that is that like if you think about plus and minus in terms of a real line, like plus 1 means you go forward. Plus 1 means you go forward 1 step. Right? Minus 1, like it doesn't mean you go forward minus 1 step, but it means you go backward 1 step. You start from 0 and then you go backward 1 step, so you end up at this point. So what you reverse is not the number. You cannot do something for a negative number. But what you can do is you can reverse the operation. Instead of moving forward, you move backward instead. Likewise, what we have here is we don't, you don't put the minus 2 here. And what we do is we reverse the process. What process? It's a process of multiplication. And what's the reverse of that? We divide. Use division. We divide m by 2 times. So that's a way to interpret this statement. M to the power of minus a. Now you divide m by 2 times. Then you reverse the process. If you multiply to get a high number, you divide to get a smaller number back to the origin number. And what this means is you divide that 2 times. If you follow the step written this way, it needs to be that. But of course, I'm sure if you knew this already, you would scream that, wait, isn't it this way? Shouldn't it be 1 over m times n? You are right, but that's not how it is defined. It is defined as a repeated division. But then, of course, only after this we can, use some property to realize that, this translates to that. So yeah, the correct way of interpreting this is this operation. But it just happens to be the same as that, which also happens to be 1 over m squared. So you can kind of see, like from this example, that, okay, m to the power of negative number, that should be m to the that number, like in the positive part, right? But you just flip from multiplying to division, multiplying to dividing. And yeah, based on this, you can see that for any number a, you should get the same pattern. M to the minus a is 1 over m to the a. But again, this is from the observation. It's not a theorem yet. No, just it should be this way. But the correct way to prove this is to notice that we can use the property we just have, which is the addition. So you don't know minus a, right? But we know that if you add that to a, you get a minus a, which is 0. Or I should write this way. M to the 0 is m to the a plus minus a, because that's 0. And then since we add exponents together, then we can use the property that we can split this into 2 parts. And the first one is 1, because m to the power of 0 is 1, which is what we just proved. And lastly, we want to find that, so we have to use algebra to to move stuff around. And there it is. This is the proof. What we have on the left is observation, but the proof is the yellow part, which is that, okay, for these two works, like m to the power of minus of m to the negative power, it must be the reciprocal, or the inverse of m to the positive power. So these are all the properties that we can then summarize as, these 5 properties, which again, I could throw this at you and ask you to do problems, but I think it's more interesting and more fun to discover that from the definition alone. Caution. There's some caution, which I forget what that is about. Give me a moment to see what I wrote. Caution. Okay, there are 2. First, like if m is not the same as n and a is not the same as b, right? Then if you have m to the power of a times n to the power of b, then these two cannot be simplified. If the base are different and the exponents are also different, then you cannot simplify that. Unless you do some magic trick, or change the base or change the exponent to match, but you can combine that. You can simplify that. Like for instance, if you have 2 to the 5 and 3 to the 0.7, then just leave it like that. There's nothing to do here. But for instance, if you have 2 to the 3 and then 4 to the 5, even though they are all different, right? There's a way to change the base to match. So this is 2. You can change 4 to 2, but it has to be 2 square. Okay, now they match, but we have to use some properties to make sure that the exponent are just a single number. And if you raise to the power twice, right? That's the same as multiplication. That's one of the property above. And then we should Not we can, but we should get 2 to the 3 times 2 to the 10, which can be now can be simplified as 2 to the 13. So this works if you can find a way to change the base to match. Let's say that's A, that's B. Like, oh, C. Okay, that's another example. Suppose you have 2 to the 6 times 9 to the 3, for instance. Again, the numbers don't match. Like the base are different and the exponents are also different. Right? But notice that 6 and 3 are pretty close. And here we can make that to be a power of 6. Now we start from converting 9 to 3 square. And because to make this a 6, we need something square. So that once we use the property 2 times 3 would give us 6. So now we have 2 to the 6 times 3 to the 6. And now we can use the property. Okay, if there are 2 copies of 2, 3 copies of 3, then, if there are 6 copies of 2, 6 copies of 3, then you can lay them on top of each other and get 2 times 3 copies of 6 copies of 2 times 3, which is 6 to the 6. So that works. Again, if there's an easy way to change the base. So that's one caution or one remark. The second one is called the freshman's dream. this interesting name, freshman's dream. And the second one, it says that if you have a plus b square, freshman, if you are a freshman and if you are not familiar with doing math, then almost everyone would distribute square or the power of 2 into the parentheses, which is not the way it works. If it works, then it should be easy. But yeah, that's not how this thing works. And because you should actually use the definition, and this is a plus b times a plus b. There are 2 copies of addition. But here you can see that since this is a plus, this is addition, this is multiplication, you cannot switch them around yet. But what you can do is you can distribute the terms. So if you use the distribution property, you should get a times a, the pink one, and then a times b, and then b times a, and then b times b. It should give you a square plus ab plus ba plus b square. If you simplify that, you should get a square plus 2 times a times b plus b square. This is the correct way to distribute this square over sum. Because as we see, if this were a product, then yeah, you can do that. For the product, you can do that. But for the addition, you can't. Okay, let's see some examples, and yeah, you can attempt the exercise yourself. Simplify the following terms using properties. I actually think I spoiled that. Oh, yeah, let's do it. So we have 3 to the power of 4 times 3 to the power of 5. So suppose you don't use any property, and you expand everything out, you will get 4 copies of 3 for the first term, and then 5 copies of 3 for the second term. If you don't use property, that's all we have. And then you can count. Oh, actually there are 9 copies of that. So the answer is 3 to the power of 9. But of course, I suggest you use a property. 4 plus 9. But maybe if this is the first time you do this, you might have to, justify, say that why you can use this property. And you can use this property because since the base are the same, then you can combine the exponents, combine the number on top using the addition. So that's A. And what about B? 2 to the power of minus 2, 2 to the power of 3. And then again, you can do it. You can do it by hand if you want to. This should give you 1 over 2 square. And that's 2 to the power of minus 2. And this one gives you 2 to the power of 3 on top, and then 2 square at the bottom. And if you use algebra to cancel terms out, the result is 2. So that's the answer. But again, you can use the same property because the base are the same. So you get 2 to the power of minus 2 plus 3, which is 2 to the 1, which is of course 2. So that's B. But C, we use different properties because now the base are different, but the exponents are the same. So you would write since the exponents are the same, or since they match, then we can combine the base. But here, notice that the when you combine the base, we combine with the multiplication, like not addition as we have earlier. And because again, you have to think about what it means for the exponent to be a sum of two numbers, what it means for the base to be a product of two numbers. And that gives you 6 to the 7. Again, it's done. Let's see. And lastly, yeah, I spoiled it already. You can see above here. Let me write it again here. So usually the base, since the base and the exponents do not match, usually you can't verify that, but we can see that, oh, actually you can translate them into the terms where the exponents match is in the way 3 to the 6 times 2 to the 6. So that's 3 times 2 to the 6, similar to what we have on the left. And the answer is 6 to the 6. These are the answers for this example. Okay, and now we can do the exercise one. All right. See you in the next section.